Hi, this is Mrs. Vrobel. This is part 3 of the matter, its property, and changes. And we talked about, with the first video, about elements and the fact that some of the elements are molecular or diatomic. Then we talked about more substances, and we talked about compounds. We talked about the difference between a heterogeneous and a homogeneous mixture. So now what we want to do is we want to talk about properties of matter in order to be able to identify what type of matter we're talking about. Now, these properties are characteristics. So when you're classifying matter, you want to make sure you pay attention to certain characteristics within those properties. And the most familiar one is probably the physical properties. So that means that you know the identity of that matter, and there's no change in composition. So a physical property, we're looking at the identity not changing and composition. So composition means what are the atoms that are contained within that matter. Now when you're looking at physical properties, probably one of the ones that you're most familiar with is essentially the odor. So lots of times you can smell something. You know, vanilla essentially smells a certain way. Sorry, I was going to add something to that, but now I can't think of it. Also the phase. So is it a solid, a liquid, or a gas? Then you might notice that there's a certain texture that you can describe with the property. For instance, you may notice that with salt, so remember I was talking about the Szechuan pepper salt, the salt crystals have a certain texture or a certain design to them. Color too would be another way of describing the matter. I'm assuming that a sugar cube, you know that it's white, just something that's typical of sucrose. Now, the ones that you might not be familiar with are things like boiling and melting points, and we're actually going to look at those in detail in a moment. And then lastly, density. Density, you can easily obtain that in the lab. You just need to know the mass of the matter and then the volume. And with that, you could calculate the density and you can apply that to a known value that has been determined in the lab. Okay, so here are some physical states of matter. So we know what solid looks like. We know what liquid looks like, and gas. So here's my fizzy water, and notice that there's some bubbles within that liquid there. If you look at the microscopic view of each, notice that with a solid, these atoms are kind of locked in place. Now, don't think that these atoms are not moving. They are. They're actually vibrating on a very tiny level. So please remember, even though these atoms are kind of positioned in space, they actually are moving. All matter moves no matter what. We're hoping that when we get to absolute zero that we can detect no motion whatsoever, but we haven't come to that yet. We're close, but we're not exactly there yet. Now notice with liquid, the difference is the molecules or the atoms are not stuck in place. They can move around. They kind of like glide past each other. So if you want to think of two swimmers that are swimming past each other, assume that these atoms have that kind of freedom of movement. And then lastly, we have gas. So gas has the greatest amount of movement. So when I'm shaking up my water, you could probably see the tiny bubbles, how they can just like fluctuate and dance throughout the liquid. So gases have the greatest freedom of movement. They're constantly vibrating, they're constantly colliding with each other, and they're probably the most vigorous out of the three phases. Okay, here we go. Solids. So looking at a sugar cube, so we have a solid which has a definite shape. It has a definite volume. It's not compressible, so I can try squeezing the sugar cube. It feels like it gives a little, but it's actually my fingers that are giving a little. It's not the actual solid that's giving. They are tightly packed together. So in this picture here, you have alternating salt crystals, or salt atoms, I should say. So the big green atoms are the salt, the little tiny pink or purple spheres are chlorine. So you have an alternating pattern of those atoms. And with sugar, it's similar but different. So there's definitely less space between the different atoms. Now, with solids, they have a very strong attraction, and eventually we'll start talking about that attraction. In order to get them to go into another phase, we have to overcome that force of attraction. So that's why some solids will melt faster than others, and that's because the attraction is weaker if they melt quicker. Okay, so liquids. So notice that this bottle of vanilla, there's no definite shape. The bottle, depending on how I move things, the liquid will accommodate that container. There is a definite volume. So on each bottle that you buy of vanilla extract, it contains a certain amount of volume. Slightly compressible. So if I wanted to, I could put this in a device that would try to squeeze the liquid. There's just tiny, tiny spaces that we can use to compress the liquid. Notice that the particles are mobile, they're able to move around, just like I said, the swimmers swimming around each other. Molecules within a liquid typically do that. Now, with liquids, it's a lot easier to get it from one phase to another. So because the molecules aren't like right up against each other necessarily, they kind of have a weak interaction. And because of that weak interaction, we can take that liquid and move it into another phase. Okay, so gases. Gases. I know this is not a great representation, but the fact that when I shake up this bottle full of fizzy water, I'm essentially causing the gas to expand and come out of the liquid. So there's no definite shape, there's no definite volume. So when I'm blowing up a balloon, that air that I'm putting in the balloon, it will take up as much space as it can possibly. I tell a lot of my students, think of it as you have two relatives that don't get along with each other, and they essentially occupy the widest position within the room because they just don't want to be near each other. Gas molecules are the same way. They're compressible. So if I have a balloon and I want to shrink it down, I can push on the outer container and eventually the gas will come in closer to itself. Also, the particles. So in a gas, the atoms or molecules, they want to be as far apart as they can compared to the space that they have available. So it's just like talking about those relatives. And then lastly, they have the weakest attraction with each other. So gases, there's not a whole lot holding them together in that space. So because of that, the forces between the gas molecules are essentially very weak. Okay, so here we have three phases, and notice that with gases, you could probably highlight this. There is the least organization, so just think of it as a messy room. The gas molecules have no semblance of order. They're just random, the way they organize themselves. Whereas liquids, we're talking about a partial mixture of atoms. So we're looking at a little bit more organization, but not very much. And then lastly, with solids, we're talking about complete organization. So you can say that like the sock drawer is very well organized for solids. Whereas liquids, they're kind of thrown all over the place. And then gases, forget it. It's a complete mess. You don't even have pairs of socks together because everything is just random. Okay, so here is a table that contains some of the physical properties of matter, and we'll just highlight a few of these. So here we have chlorine. I don't know if you've ever seen chlorine gas. You may have seen it on YouTube or something like that. It typically is yellow in color. If you ever happen to work at a pool, they sometimes use chlorine gas to chlorinate the water. You'll notice that the gas is yellow. Now, obviously, you do not want to be inhaling chlorine gas. It's really nasty. It's deadly. So notice that it's a sharp, suffocating odor. Chlorine typically is in the gaseous state. And because it's the gaseous state, notice that its melting point is a negative 101 Celsius. So it does not like to be orderly and in the solid state. So it occupies a very extremely low melting point because of that. Water. Well, water, and this is something that you've seen numerous times and you're very familiar with it. It has no color. It has hopefully no odor unless you happen to be near well water. Well water will have that odor, and that's because of the minerals that are associated with that well. It should be tasteless. Notice that it is a liquid state, and because it's a liquid state, its melting point is actually much higher. So it has forces of attraction that are stronger than the gaseous phase, so its melting point should be higher. And notice its boiling point is significantly higher too, and thankfully, otherwise we would have problems on this planet if we didn't have a high boiling point for water. Then lastly, let's look at sugar. We know sugar is white. If it's not white, you know that probably it's containing molasses, which is brown sugar. If you're like me, you like to have raw sugar. Same thing. You have an added component to that sugar to give it that brown color. It should be odorless. If it isn't, there's probably another substance that is in that sugar. Notice that it tastes sweet, and the difference is it is solid. Because it has a stronger attraction with itself, it's more orderly. That's why it occupies the solid state. I am not sure why the melting point isn't included here, but notice that it should be higher than 0 Celsius, and we know that for a fact it is higher. Okay, I believe this is my last slide that I want to talk to you about. So here we have phase changes, and I'm going to list the types, and then together we're going to work on the name for them. Okay, so the first type here, we have liquid to solid. So if you had to guess, what phase change do you call it when you go from liquid to solid? Okay, so hopefully, oops, sorry, I'm going to get my pen out. And I'll just leave that there. Okay, so hopefully you figured out this is freezing. That's a Z, by the way. Okay, the next phase change, we go from a gas to a liquid. This one you may or may not be familiar with. Condensation. So you know when you see dew forming on the grass, or you're taking a shower and there is moisture on a mirror, that's essentially condensation. Okay, the next phase change, solid to liquid. Yay! I would think everybody knows this one. Okay, liquid to gas. This should be another familiar one. Okay, this one may or may not be familiar to you if you're going from a solid phase to a gas phase. Now, as we're skipping a step, this is called sublimation. So we're talking about dry ice. Ice cubes actually do this too. You'll notice over time that the ice, when you initially made it, there's not as much solid as it originally was over time. And then lastly, gas to solid. Skipping a step. We call this deposition. It's depositing a solid on a surface, hence the term deposition. Okay, so those are all the phase changes that you need to know, and don't be surprised if you see this on the video assessment. And then lastly, if you are making a solution, so if you are essentially creating vanilla extract, you are forming a solution, and that would be also considered a phase change, where you're taking a solid and maybe converting it into the liquid phase, or you could be taking a gas and putting it into the liquid phase, like my fizzy water. Okay, so be ready for the video assessment tomorrow.